All right, so we're going to talk about energy quality. So from the first law, we've learned that energy can neither be created nor destroyed. It is what it is. There's a finite amount of energy throughout the whole universe. And when we watch nature go through her tricks, as Feynman says, the amount of energy we measure before an energy conversion or some kind of change is identical to the amount of energy after that change. So when I lit a match on Wednesday, the amount of energy contained in that match is the same as the amount of energy that spread throughout the entire room via heat and light and particles of you know volatile organic compounds, stuff that you should not breathe into your lungs. Um, Second law tells us that the quality of energy changes over time. That without constraints, energy tends to disperse throughout the universe, and that with any energy conversion, you don't have 100% conversion of one type of energy into the other type of energy. Some waste heat is produced, some friction happens, some sound happens, some vibration happens, and you have energy being lost. Uh, it's still there, it's still energy, it's just no longer useful. And so this lecture, we're looking at what makes energy useful or not to society. We want energy to do something for us. We want it to heat our coffee, um, dry out our rotten ceilings, move our cars, fly our planes, run Zoom meetings, etc. So what makes energy useful? That's what we'll look at today. This is Seneca. He's a philosopher of. He's one of the first philosophers to write about transcending good and bad. If you think of like Nietzsche talking about beyond good and evil, he had some of those ideas 2,000 years earlier. He was thinking about there isn't just good and bad. We can measure other aspects of things. Uh, he's born at a very strange time though, 4 BC to AD 65. When he was zero years old, he was actually 4 years old, I guess. I don't know. Something crazy happened then. There's apparently an eclipse and earthquake and stuff. Anyways, um, okay, so today we'll learn that not all jewels are created equal in terms of their usefulness to society. We'll learn about the ability to do useful work, and we'll introduce exergy as a cartoon concept. It's really a very highfalutin, nerdy, grad level thing, but I think it's a fun concept to think about and useful to think about. Okay, so last time we learned about this energy quality ladder. And this is all just a description of how easily some form of energy is to be constrained. So electricity is very easily constrained. You put it in a wire. Mechanical energy is very easily constrained. You use belts and gears and chains to transmit mechanical energy. Chemical energy is fairly well constrained. There are things like activation barriers and different thermal losses in chemical processes, but in general, something like a battery can be very efficient, at like 90 degrees efficient. And then we're at high temperature where it's fairly well constrained. You can steer high temperature fluids and gases to do things you want, like push a piston, for example. But by the time you're down to low temp, it doesn't do anything. You can't get it to do anything at all. Maybe an RTG with very, very low wattage, very low power. Going down this ladder, conversions are very efficient, meaning the amount of lower down energy you get versus the amount of energy you put in is very high. Going up the ladder is very inefficient. So there's this cool chart from Man, Energy, and Society that looks at all sorts of different energy conversions. Here's efficiency on the y-axis and different conversions. If it's an uphill conversion on that ladder, it has 1 star. If it's a downhill or level conversion on that little ladder, it has these 2 stars. So let's look at an uphill conversion. Thank you. I got a secretary today. It's awesome. She actually runs the house. I'm more the secretary. Okay, so thermal to kinetic would be an uphill type deal. So a thermal to kinetic would be like a car piston. And so if we look at these different black lines, we can see what it's talking about. So this is aircraft gas turbine would be thermal, liquid fuel rocket. That's chemical to thermal. So what's this one? I guess it's liquid fuel rocket as well. That'd be thermal to kinetic. Thermal to electrical, that's that RTG, terribly inefficient. And so that's like 7 to 8%. And then, yeah, we can look at different things. Electrical to radiant. So this is interesting. Back in the 70s, you had things like an incandescent lamp, which is like 5 degrees efficient, terrible. Better yet were things like fluorescent lamp. That was about the best you had back then. These other lamps were more special things. But today we have LED lamps, which are 50 to 90% efficient. The ones that you screw into your house light bulb is about 50% efficient, but you know, an LED on the small ones on like computer components or car headlamps and stuff can be up to like 90% efficient. So huge leaps in efficiency there from electrical to radiant. Incidentally, these incandescent light bulbs can be used as space heaters in your house. If you live in a really cold climate, some people prefer to have these incandescent lamps because they heat your house at the same time. But it's still far less efficient than using something like a heat pump to heat your house. So yeah, have a look at this. There's all sorts of interesting things to piece out of this. And the different labels on the side are interesting. All right, so again, the equation for efficiency, eta equals useful output over energy inputs. Another way of saying that would be what you get over what you pay. So let's look at that for a second here. What am I trying to talk about here? Okay, so the cool thing about efficiencies is you can chain them together. So if you have one energy conversion to another, to another, to another, to another, you just multiply all those numbers that are less than 1, between 0 and 1, by each other. You don't multiply the percent signs next to each other. So you know, something like 90% really means 0.9. That's what that fraction is. It'd be 9 over 10 or something. So you can take all those efficiencies and chain them together when you're going through multiple energy conversions. So this would be a coal power plant over here on the left. It has a efficiency of 35%. So you light some coal on fire, you boil water, you make steam, it spins a turbine. That turbine's connected to a shaft, which spins a generator. That generator generates electrical current. So even this system here has several different conversions along the way that lead to an overall systems efficiency of 35% or 0.35. The lossiest one is the one that goes furthest up the ladder. So which process goes furthest up the ladder, do you think? Electrical? Yeah, that end result. Yeah, maybe I phrased that question poorly. Electrical is definitely the furthest up the energy ladder, but which conversion going from one type of energy to another is going furthest up the ladder? So we have chemical to thermal when you're lighting the coal on fire. So you have some chemistry, you react it with oxygen, you make heat. That's going to be really efficient. That's going to be like 100% efficient. And then you have thermal to mechanical when you take that hot water that's turned into steam and start spinning a turbine. So that's thermal to mechanical. And that's actually where chemical to electrical, yes, but there's a few conversions within that thing. And that's what I'm talking about. So you have chemical to heat to mechanical. And that heat to mechanical is where you had to climb that ladder very, like, nearly all the way up from high temp to mechanical. And that's where the losses happen. So a tremendous amount of waste heat ends up just going up this smokestack. When you look at a coal-fired power plant or a gas-fired power plant, there shouldn't be smoke coming out. What should be coming out is just CO2 and water. because coal and gas and things like that are hydrocarbons. They're made out of carbon and hydrogen. They react with oxygen and make CO2 and H2O. And so it should just be a steam cloud coming out of there, and that's what you see. You see something dirty, then that's the terrible power plant that needs to be cleaned. Same with even things like a wood stove. You should just be having CO2 and steam coming out of them. The more smoke, that means the wetter the person's wood is, or the crummier the stove is. All right, so this power plant is 35% efficient from going coal to electricity. And then that electricity is sent over transmission lines. They're not perfectly efficient either. They're about 90% efficient. You can hear them humming. They generate heat, all sorts of things like that. So not all the energy gets carried across those wires. And then it goes into your house. And if you have an old-fashioned incandescent light bulb that apparently is the size of your house in this example, it's only 5% efficient. And so the overall systems level efficiency, you achieve that number by just multiplying everything together. So the efficiency of the power plant multiplied by the efficiency of the power line multiplied by the efficiency of the light bulb, 0.35 by 0.9 by 0.05 equals 0.016. This sucks. It means that all the energy in that coal, if you had 1 kilowatt hour worth of coal, you only get 0.016 kilowatt hours of light. So the amount of useful energy you get, the light, is at 1.6%. That means what? Like 98% of that coal was completely wasted. It just turned into heat that slowly heated up the universe, completely useless. So it's really important to think about systems level efficiency, not just the efficiency anywhere along the line here. And it also means that things you do in your house can make a big difference. If you put in a LED light bulb at like 50% efficiency, now all of a sudden your personal coal use is going to go down by a factor of 25. 50 divided by 2, or it'll go down by a factor of 10. 50 divided by 50 divided by 5. So you'll use a tenth less coal if you just swap out a light bulb. Huge difference. Are hydroelectric plants more efficient? Reading this from the chat. Yes, they are. Hydroelectric plants are about 90% efficient if we're talking about big like Francis turbines in Grand Coulee Dam, up to like 85% efficient if we're using like Pelton turbines in a smaller run-of-the-river dam that we have like up and down the I-5 corridor here. Wind turbines, I forget the efficiency of wind turbines. The interesting thing about wind, solar, and hydro, though, is efficiency matters, yes, in terms of like buying materials and occupying real estate, but the actual resource, sun, wind, water, it's not that big a deal. Hey, Violet, people want to say hi to you. Come stand over here.
Dad, where's Tony?
He's just hanging out.
Hi.
Hello.
So you're not really wasting something when you're wasting the wind, except the resources required to harvest the wind. We'll talk later on, way towards the end of the class, we'll talk about something called net energy analysis. That's another thing that I study. How much energy does it take to get energy? And wind's amazing. You build a wind turbine, say it costs 1 unit of energy, you get about 120 units of energy back. Hydropower is even better because it takes a lot of energy to build a dam or a turbine, but then it just runs for 100 years and you continue to harvest energy. Whereas something like a coal power plant, it takes some energy to build the coal power plant, but then you have to continue to use energy to dig the coal out of the ground. And so it only has an energy return of about 18 to 1. Not nearly as good. All right, so if we use CFLs, nobody uses those anymore because they make your skin and food look terrible. But this was something we tried to do like in the 2000s. Before LEDs were a great technology. So that reduces your coal consumption by a factor of 4 and increases your overall systems efficiency to 6.3. And then again, using an LED that's 50% efficient, reduce coal consumption from an incandescent by 10x, and commensurate carbon emissions, everything else. If you were given the final efficiency or final energy amount, how do you find out how much energy was lost, or say coal was necessary to bring that much energy? You'd have to know the whole system, right? but you can certainly make comparisons, right? You can look at the end use efficiency of your appliance or light bulb or whatever, and know that if you double your efficiency at your home, you're going to cut your energy consumption throughout that entire chain by a factor of 2. You're going to cut it in half. And so, this is why consumer decisions and the efficiency of their appliances can make a really big difference. There's after the Fukushima Daiichi disaster in Japan, when the tidal wave came and sunk a reactor, and Japan decided that nuclear energy was not something they wanted to rely on anymore, and they shut down their nuclear power plants. They're like, oh shit, we got to build a bunch of gas power plants now to make up for this huge loss. But luckily, there were smart system level thinkers there that said, well, 1 gigawatt nuclear power plant is the same as 100 million light bulbs. So let's just swap out 100 million light bulbs instead of building a power plant. And that's what they did. They really focused on energy efficiency throughout the country. And so they didn't need to build nearly as many power plants to replace the nuclear power plants that they decommissioned after Fukushima Daiichi. I mean, it's just an equation, right? Supply and demand. You can adjust either the supply or the demand, and they adjusted demand without suffering quality of life. The useful energy was the same. How does swapping out a light bulb make something more efficient? If you change the type of light bulb. So an incandescent light bulb, the old-fashioned glowy ones, they're only 5% efficient. So if you run that for an hour, you will use, so it's a 60 watt light bulb, right? You will use 60 watts multiplied by an hour. Energy equals power times time. So you use 60 watt hours over the course of that hour. But if you swap it out with an LED that's only 2 watts, now you're using 2 watt hours instead of 60 watt hours over the course of that hour. So you swap out, you take the exact same energy service you want, in this case, lighting, or it could be something like a TV or I don't know what else. I mean, a vehicle that gets better gas mileage will use less gasoline to go the same distance. So you have the exact same energy service, transportation, lighting, whatever, but you just use far less energy to achieve that desired effect. Okay, we can talk more about efficiency. We'll talk about it the whole rest of the class. But another form of energy quality that I wanted to talk about was energy density. And so this is becoming really important for transportation. So how many kilowatt hours or how many joules can you pack into a battery for an electric car to alleviate something called range anxiety? So a Nissan Leaf, a great car, but it only goes 90 miles. And that's if you pretend the gas pedal's an eggshell that you don't want to crush. And so it'll get you to Seattle, but it won't get you home. Something like a Tesla 3 will get you like 250 miles. Tesla S will get you like the 100 kilowatt hour one will get you 350 miles or something. And so packing as much energy as you can into a space or a unit mass has become really important. And so this chart actually shows 2 different densities here, specific energy density and volumetric energy density. So the energy density could be something like megajoules per kilogram or megajoules per liter or megajoules per cubic meter or something like that. Maybe a very automobile type energy density, and these are absurd units, but it might be kilowatt hours per car. And so a Leaf has like 33, my plug-in hybrid has like 14, a Tesla has 100. And so a Leaf can go 90, my car only goes like 30, and a Tesla can go 330 miles or so. So here's a bunch of different things with different energy densities. Here's gasoline. No, that's gasohol. That's what you make from corn. You can make whiskey, or you can make ethanol, gasohol. Where's gasoline? Here's gasoline right here. Let me quit annotating. My dad was talking about the rocket ship problem of how Teslas are lower efficiency even though they have higher energy capacity. My Leaf goes 120. Nice. You must have a new Leaf or can hold more energy. Teslas have amazing efficiency, especially the 3. It's like the most efficient vehicle available to the public. So maybe this is a little confused or something. Anyway, so yeah, Teslas get like, it's like 0.2 kilowatt hours per mile. It's incredible. Be like 180 mpg equivalent. So gasoline is up here at like 50 megajoules per kilogram. So that's crazy. A kilogram of gasoline, what would a gallon would weigh, like 3.5 kilograms or something, has a tremendous amount of energy, 50 megajoules. And we compare that to a lithium ion battery, which is what's in a Tesla, and we're way down here on the floor. So at least 2 orders of magnitude lower. And so that's a problem, right? And that's why the entire base of a Tesla is the battery pack. Whereas you can go that same 300 so miles with a Honda Civic with a gas tank that's this big, that's like 10 gallons. So the energy density of gasoline is much, much higher than batteries. The efficiency of electric cars are much, much more efficient. They're like 80 something percent efficient, whereas an internal combustion engine is only 22% efficient. Why? That energy quality ladder. You're going from chemistry to electricity in a Tesla, whereas in a traditional vehicle, you're going from chemistry to heat to mechanical. So you go chemistry, and then all the way down the ladder to heat, and then all the way past chemistry to mechanical. And so most of that just turns into heat in your car and exhaust going out your tailpipe. But there's a lot of other different things we can look at in terms of energy density. Hydrogen is incredibly energy dense, and so this is why you run things like rocket ships off of this. You actually run it off of hydrazine, which is a way to kind of contain the hydrogen in nitrogen bonds. But let's not talk about that. But so hydrogen is an incredibly dense fuel. A lot of metals are actually very energy dense, just pure metals that haven't oxidized yet. You can look at things like magnesium and phosphorus and things like that.
Wait,
are very yeah.
How would you get like the energy from the metals? Like how do you, I don't really get it. Like
Yeah, so so something like iron will rust over time. It'll react with oxygen in the air and slowly turn red. And that's actually an exothermic reaction. It's producing heat when that happens. It's just very, very slow. The reaction, the kinetics of iron reacting with oxygen are very slow. The energy's there, the power isn't. Something like magnesium or phosphorus. Is phosphorus on here? It's not. These things have very rapid kinetics, and that's why you can make bombs with phosphorus. It's a war crime. It's illegal, but it will rapidly react with water. It'll steal the oxygen out of water, and so that's why it's a war crime. You drop phosphorus from the sky, and it reacts with the water in people's skin and burns them horrifically. So yeah, it's that chemical reaction with oxygen that allows these to be very energy dense. These different metals. Same with lithium. It loves oxygen, zinc, all these things. Pure lithium's way up here. Hydrocarbons are wonderful fuels because they're metastable. It's carbon combined with hydrogen, and they don't just catch fire spontaneously. You have to heat them up a little bit, and then they go critical, and then they exothermic can provide their own heat to continue the reaction until the fuel is consumed. But that's what's so great about hydrocarbons. We're able to store them in barrels. We're able to pump them through pipes, and they don't catch fire unless there's a spark. Yeah. All right, so that was a little bit about energy density and why we use things like hydrocarbons throughout society, and why this transition to pure renewable society based on renewable electricity sources like solar and wind and battery storage is challenging because we have to sacrifice this huge difference in energy density. Luckily, we can use things like efficiency to make up a lot of ground, but this is current challenge with technology. It's fighting this energy density battle. Okay, let's clear these annotations. Okay, let's talk a little bit about exergy. So all energy systems start with some primary energy resource, wind, solar, coal, oil, and convert it to some more useful energy service. That's what the whole energy industry is, right? We pump, that's what fracking's for. We're trying to get a useful primary energy source, in that case gas, and then transfer it into some useful energy service like heating your house. All energy conversions are less than 100% efficient. We know that from the second law. Well-engineered systems can exceed 50% of theoretical max. And then, so this example, internal combustion, that's what IC stands for, internal combustion engine. Primary resource is petroleum. We convert that, we upgrade that to gasoline in a refinery. There's one north of us in Cherry Point. There's one south of us at March Point in Anacortes. And that conversion is about 85% efficient. Then we put it in the engine, and that mechanical work is only 16 to 32% efficient. Most of it's waste heat. The mechanical work actually going to your tire is probably about like 95% efficient. And so the total so-called well-to-wheel efficiency, that's what they use. It's a clever way to describe systems level efficiency for an automobile, going from the oil well to the wheel spinning in your car. It's only about 14 to 27% efficient for a car. Generally, systems with fewer conversions can be more efficient. We talked about a little bit that last time. And here's some average conversion efficiencies for power generation. Okay, yeah, here we are. Wind is 50%. Nuclear, 30%. Again, they don't run as hot as a coal power plant for safety, and they have all these pumps running fluids to keep it cool for safety measures. So it's not quite as efficient as coal power plant. But the original resource doesn't produce CO2 like coal does, so it's very beneficial that way. Natural gas, a peaker plant, which is basically just an airplane engine turned on its side. That's what we have downtown, for example. They can be quite efficient. An old one is going to be like 30% efficient. A state-of-the-art one, so-called aeroderivative, literally based off of airplane engines, are about 45% efficient. That's what we have downtown. They can get as high as 60% efficient doing something very clever. You take the exhaust out of the turbine and use that to boil water, mix steam, and then run a secondary turbine. And you extract a little bit more electricity from that waste heat from the primary turbine. Wind 50%, solar 15%. It's pushing now like 18%. Crazy different multi-junction solar panels can get above 50%. We'll talk about that at another time. But exergy is this cool concept. It's a measure of the useful energy from an energy source. So exergy is the useful portion of energy that allows us to do work and perform energy services. Energy is conserved, but exergy is not. So you have the certain amount of exergy contained in the gasoline for a car, or a certain amount of energy, I meant to say, you have this chemical energy in the gasoline, but the actual useful portion of that gasoline depends on the system you're operating and the environment you're in. And so the exergy is something that's present, and then you burn through it, and the exergy is no longer there anymore. So exergy is available only in materials and fluids we call resources. Is converted into exergy carriers, convenient to use in our homes, vehicles, and factories. You always need some baseline, relative baseline. So something like boiling water at 100 degrees Celsius has a lot of exergy in this room that I'm in at 20 degrees Celsius. If this room, well, I'd be dead, but if this room was 100 degrees Celsius too, it has zero exergy, because there'd be no gradient established. It'd be the same temperature as everything around it. And interestingly, the more exergy you have with temperature depends on that temperature difference. What's another way I can talk about this? Sorry to use a planetary science example, but I'm a planetary scientist in a former life. So something like gasoline or methane has a tremendous amount of exergy on Earth because we live in an oxygen-rich atmosphere. So these hydrocarbons can burn in oxygen and create energy. There's a chemical energy gradient available to us. If you took that methane to Titan, a moon on Saturn, which has lakes of methane, it would be completely useless because you couldn't light it on fire. If you wanted to bring exergy to Titan, if you wanted to bring a fuel to Titan, you wouldn't bring a hydrocarbon. What would you bring? Oxygen. Yeah, exactly. So oxygen would be the fuel in a methane-rich planet, whereas we're an oxygen-rich planet, so hydrocarbons are the fuel. So is exergy just the overall efficiency? Yes, but it depends on what your energy conversion is and the environment that it's present. So a coal power plant is going to be more exergetic operated in a cold climate because that temperature difference is higher. So you can create a bigger delta there. It's just a cartoon concept to think about. It kind of ties together the first and second law to think about how much useful energy you can extract from a particular system. All right, we won't dwell on it though, but I just wanted to use it as another way to think about what makes energy useful versus useless. It depends on what you're using it for and the environment in which it's being used. Okay, little vocabulary. What's a resource? We define resources as either reservoirs or streams in energy and society. And so reservoirs are things like fossil fuels, oil fields, coal seams, gas fields, forests, uranium-rich ores. And streams are things that we tap into. So you can think of this as energy and this is power. This is energy over time, right? So we can tap into kinetic energy streams, wind, ocean currents, rivers. I forgot to write that there. Gravitational potential, that'd be tides and rain. And then heat conduction, which would just be geothermal reservoirs, areas of hot earth that's near the surface. So we have reserves and streams. And the big trick right now that we're trying to do, and your generation is going to have to figure this out, is going from reservoirs, things we can stack up and pile in big tanks or, piles of coal, to streams. How can we go from, storing energy to just tapping into it in real time? We should be able to do that. We did it for a good 199,700 years of human society. It's just in the last 300 years we started stacking it all up and pulling it out of the ground. And so we'll have to learn how to be more fleet-footed again if we're going to avoid catastrophic climate change. Okay. We classify them as along their replenishment timescale. So something like fossil fuels. The reason they're called fossil fuels is because they're only replenished over the course of 30 to 60 million years. It takes about 30 million years to make oil, maybe 10 million years to make coal. It takes tremendous geological time. So all the carbon we're putting in the air right now will be helpful to some society 60 million years from now because it's increasing biomass and making oil in the future, but it's not very useful to us right now, nor to all the other species on the planet. What makes something a renewable is having a very short time scale, replenishment time constant. So solar radiation, milliseconds, wind, wave, these things, hours. OTEC is ocean thermal electrical current. You can take advantage of temperature contrast in the ocean and create a small electrical current. Not very high energy density, so not useful yet. Why does geothermal have both days and none? Yeah, that's the difference between dry and wet geothermal systems. So a wet geothermal system, something like Yellowstone or Geyserville down in Northern California, it has porous rock near some volcanic activity, and so water continues to flow and circulate and create a bunch of hot water that's continuing to flow that you can continue to tap into. Same with Iceland, right? Dry rock geothermal would be something that would be present in Nevada, for example, where you have, um, uh, basin and range systems where the continental crust is stretching out. And in those basins, you have hot rock, but it's dry as a bone. And so to actually extract that heat, you have to frack it. You drill a pipe, you frack that rock to create cracks in the structure because it's not porous and permeable like it is in Yellowstone or Geyserville. And then you inject water, your working fluid, to extract that heat, turns it into steam, and then you run a turbine with that. As soon as you cool the rock down with that water over the course of 10 years or something of operations, you can no longer get any more heat from that rock. You have to move your plant or pipe a mile down the road and frack a new region. And so the permeable porous geothermal systems are replenishable on days. The non-permeable, non-porous, non-wet geothermal systems are not replenishable. Yeah. Fission fusion, I mean, I guess it's replenishable over like 5 billion years. That's like the life of a star, but not useful to society. Okay, this is my favorite chart of the whole class. Study it up for a couple minutes and we'll have a test.
I'm gonna cry.
No, so this is the whole game. This is the whole thing. This is what's available to planet Earth and human society writ large. This is all the exergy available to us. So let's parse through this slowly. This is called a Sankey diagram, where the size of the pipes or the flows are relative to the amount of power that's running through them. Let's put things into perspective. We currently use 18 terawatts, all of the Earth, all of the humans on Earth. So if I had one of those kilowatt meters I showed when I boiled coffee, we plugged in all of society to a kilowatt hour. A kilowatt meter, it'd say we're burning 18 terawatts on average. So that's all our cars, all our planes, all our houses, all our buildings, all our everything going at once is 18 terawatts of power. So if we look at how much sun is hitting the top of the atmosphere of the Earth, that's 162,000 terawatts. And so 18 is here. So we have enough exergy to run society 1,000 times over, just from the sun reaching the planet. So we can grow our society by 1,000x in terms of energy use. So we are completely fat in energy. We do not have an energy shortage. We have an energy acquisition shortage and an energy equitability distribution huge shortage or problem there. There's a lot of disparity in who has access to energy and who doesn't. So of that 162,000 terawatts hitting the atmosphere, a lot of it gets reflected. 34,000 watts just bounce off the atmosphere. 31,000 gets absorbed. What does that mean? It turns into heat in the atmosphere. That's useful. It creates weather. It creates wind currents. We can tap into that. So of that heat, 870 terawatts gets turned into wind. Right now we're harvesting, which is probably about 10x this now. We're harvesting about 0.6 terawatts of wind energy today. And so even with wind, we can grow that by 1,000x. I mean, I'm sure there'd be some problems with covering the entire planet with wind turbines, but there's no shortage of wind. Certainly no shortage of solar energy. And so let's look at solar energy. How much are we harvesting? Okay, right here. So sun hits the atmosphere, some is bounced off, some is absorbed, turned into heat and wind. Some of it reaches the surface, 86,000 terawatts. A lot of that, 41,000 terawatts, goes into evaporating the ocean, making clouds, making rain. So here's the clouds. We got 90 terawatts of power in the clouds, 5.5 terawatts of power in our rivers. And right now we're harvesting only 0.36 terawatts. And so we could certainly acquire much more energy from our rivers. We may not want to do that for environmental reasons, but there's huge opportunity there. But my money is on solar. So 43,000 terawatts are reaching the surface. We're only harvesting, again, probably 10 times this, because this plot was made back in 2012. So we're only harvesting 0.16 terawatts. And so we have this huge delta where we can harvest so much more energy just from solar panels, placing them in high gain areas like the Sahara or Arizona, for example. Look at, plants are just kicking our ass. Like, we're harvesting 0.016 terawatts. Plants are harvesting 90 terawatts. So photosynthesis, 90 terawatts of power running through the biosphere. So plants are just doing an amazing job. And they're a huge energy store. So these bubbles that you see on this chart is zettajoules, which is an insane number, 10 to the 21 joules. Remember that all of society uses like 500 exajoules, 500 times 10 to the 18. So this zettajoule could run society for like 100 years. Plants, 30 zettajoules of storage just in plants alone. And so we can light some of that on fire. We do. So 1.2 terawatts of societal energy use comes from traditional biomass. So, this is significant. Something like 5 to 8% of all our energy today still just comes from biomass. 300 years ago, it all came from biomass. That was the whole game, right? We would run everything off of wood, and we would feed our draft animals to plow our fields with hay and other biocrops, and so everything used to be biomass. Now it's down to about 8%. Some of it gets turned into biofuels. Over time, photosynthetic plants get buried and they turn into coal and oil and gas. And so here are massive stores of exergy in terms of coal, oil, and gas from past photosynthetic action over the last 100 million years or so. This is a freaky one, methane hydrates. Tremendous resource in methane hydrates. We'll talk about them later when we talk about natural gas. This is what scares me. If we start tapping into this, there'll be no hope in terms of global warming. Some people are worried about running out of energy. No, I'm definitely worried that we have way too much fossil fuel energy, and we'll cook the place way before we run out of energy. So here's all our hydrocarbon stores right now. Recall that society uses 18 terawatts of power. 3.6 terawatts is from burning coal. That's probably down to like 2.5 now. Most of Europe and America has gone away from coal, not because we're good people or anything, but just due to economic reasons. And but other places like India and China are increasing coal production, again, due to coal use due to economic reasons. So this is probably down to like 3, I'm guessing. Oil is beyond this now. We're using more oil than we have ever before. And so this might be like 5.4 or something terawatts of oil use. Gas is probably double this. We're using much more gas than we did 10 years ago. And gas, I'm talking about natural gas, methane, not gasoline. Okay, a few other things to talk about here. Crustal energy. So this is huge store of energy from the formation of the solar system. All those rocks colliding together, making the planet, created this tremendous reservoir of thermal energy. Not only that, that reservoir is continuing to be replenished and growing in size over time due to the radioactive decay of uranium, thorium, and potassium. And so huge store of energy in the crust. It's just deep in there. You can't get to it. Seawater uranium, 360,000 zettajoules. So this is a energy density problem, right? Same with lithium. There's tremendous, and deuterium, that's heavy hydrogen, tremendous amount of energy stores in the ocean itself, but it's just spread out super thin. So it takes more energy to scoop that up than you'd get from actually burning it. he wasn't serious about us memorizing this, right? No, not at all. But this is the game. These are the rules. If we want to grow society, promote human welfare, and save the planet, these are all the chips we have. These are all the pieces. And thinking about this is, you know, where we should start. Yeah, I think I've belabored it enough. Yeah, I just think this is fascinating. I could stare at this forever, but maybe I'm a nerd. Any questions or thoughts about this? I've seen quite a bit in the chat that I've tried to respond to. Definitely super cool and interesting. Thank you, Rosie. If only we were water benders and could move the water around to create energy and reduce wastage. Yeah, absolutely. I mean, we kind of are with desal plants and things like that at this point. Okay. Let's talk about capacity factor when we talk about renewables. Capacity factor is how much energy you can actually get from something like a wind turbine or a solar panel versus how much you actually get. So, you know, my solar panels are on my roof right now. It's a cloudy, stormy day. They could generate 5 kilowatts of power. They're probably making maybe like 300 watts right now. So even though wind turbines and solar panels can produce a lot of power, they don't always do. They, in fact, have pretty low capacity factors. In Bellingham, the capacity factor of a solar panel is about 18%. That means it's only generating 18% of the power it could do if the sun was shining on it 24 hours a day. Of course, that's not going to happen because we have night. What do I want to talk about in the last little bit here? We should really save energy systems for another time. I'll probably just cut into the oil lecture because we want to talk about how things are actually used, not stuff we want to move away from. I'll talk about engines because these are the prime movers in society. And by engines, these are things that, what is the life expectancy of solar panels? Like 25 years. These are the things that power all of society today still, where renewables are only about like 10, 12%. Most of all our energy still comes from these big engines, these big power plants. And so the main mover in society is the Rankine engine or the steam engine. You make something hot with coal or gas or nuclear fission, and you boil water. You make steam. That steam is high pressure and high temperature. And so it wants to equilibrate. It wants to disperse because of the second law of thermodynamics and become the same as the atmosphere outside. And so you constrain it with thousands of little fan blades. And so the only way for that steam to get to the atmosphere is by spinning all these fan blades. And that's what it does. You connect those all to a shaft and you can drive a generator. Efficiency of about 30 to 40%. So here's a qualitative picture of a coal power plant. Goes in here. This is the furnace. You pulverize the coal, turn it into a powder. It reacts with oxygen and heat, lights on fire, makes steam. That runs a turbine, which runs a generator and goes through some transmission lines. The other main prime mover in society is the Brayton cycle, and this is the gas turbine. Powers airplanes and natural gas power plants. The way this works is you have a combustion chamber where you burn a gaseous fuel like natural gas, and the combustion of that gas causes rapid expansion and rapid increase in temperature, highly exergetic, exothermic. That pressure and temperature wants to go somewhere. You force it out this turbine, so it spins all these blades. That turbine is connected to a shaft, which is connected to a turbine in reverse. So the fan blades are pointed in the opposite direction. And that sucks in a bunch of cold, oxygen-rich air, which increases the pressure and allows this combustion reaction to be even more exergetic. You increase the enthalpy or exergy of this reaction by sucking in high pressure, high oxygen-rich air. And so that's how this combustion turbine works. In a schematic form, it's quite beautiful, I think. Here's a bunch of turbine blades here in the compressor, sucking air in here. Here's the combustion chambers. There's all these cans, they're called, radially distributed about the turbine. And so this is where gas is combusted. to generate, again, high pressure, high temperature, forcing that high temperature, high pressure exhaust out this end, spinning a bunch of turbine blades here, and then that shaft is connected to drive this compressor. There is a mnemonic to remember how this works. It's crude. I apologize if you have sensitive ears, but it goes like this: suck, squeeze, bang, blow. And I think I'll leave it at that for today. Monday we'll have a study session, and we'll go over the homework. Are we going to need to memorize all these engine things? No, but I want you to know a little bit about the steam engine, because that's what runs all of society today. Yeah, I need you to know that you have to energy conversions. You're burning something to make something hot to run a fan, which you can hook up to a generator to make electricity. That, coal doesn't make electricity. A bunch of energy conversions along the way makes electricity. Same with natural gas. And know that these things aren't perfectly efficient. A lot of that energy is wasted due to the second law and produces things we don't want, like CO2.
Why do we need to do a study session this Monday? Do we have a test coming up?
We have a midterm. The study session is for the homework. We have a midterm sometime. Let's see.
Oh, I see it. I wrote it down on my planner since the beginning of the quarter. It's Friday, October 23rd.
Yeah, and I'll have the midterm. It'll be released the 19th and due the 23rd. So you'll have 4 or 5 days to work through it and think about it. It should, I'm pegging it to take about like maybe an hour to 2 hours, but that way you won't have any anxiety about time limits or things like that. You'll get to slowly work through it.
Well, thank you, sir. That'll give me some more time to work on the other things that I have to do for my music classes. Thank you so much.
Yeah, great. And yeah, hopefully it leaves anxiety, and yeah, we don't need to make things scary. Should we read that before next class? Read which? The EIA Energy Annual Outlook. No. Oh yeah, I have it here, don't I? Should probably just peruse it. I mean, it's a huge long document. Did I even post it yet? We should definitely look at it before the Kaya identity. That's when we're looking at societal energy use. EIA Energy Outlook, yeah, here it is. Read the executive summary, just get an idea that that people are quantifying these things. So the EIA is the U.S. Energy Information Administration, and they just think about how much energy the world is using, where the energy comes from, and what things may look like in the future. Quick question off topic. You think that the wildfires recently majorly caused by climate change have put us into a vicious cycle of greenhouse gas emissions? Not a vicious cycle, but it certainly is a feedback loop. Yeah, these were big stores of carbon that are now in the atmosphere. The thing that I'm most concerned about is destabilization of the permafrost and release of methane in the Arctic. And that's because methane is 25 to 100 times more potent than CO2 as a greenhouse gas. Yeah. And yes, we do subscribe to climate change in this class. It's been known to exist for at least 300 years, and we have records of it going back throughout all of human history. It happens on Mars and Venus too. All right.
Thank you, Charlie.
Yeah, my pleasure. See you guys Monday.
Thank you, Charlie.
Adios. I'll keep on hanging out in case anybody has questions.
I have a question about deuterium.
About deuterium? Yeah.
How is it theoretically possible we can harvest it in like an efficient way?
I have not given it much thought.
No.
It's not ionic, so you can't attract it with electromagnetism.
Mhm.
It's the second smallest element in the universe, and so you can't catch it with a net, because any net you have is going to be, the holes are
It's-
going to be bigger than it is. So
It's just like a different ion of water, right?
yeah,
Okay.
it's one of the hydrogens has an extra neutron on it. So protons determine the flavor of an element. So a hydrogen has one proton, and water is H2O, and then maybe there be a slight polarization difference, but we're talking about 10 to the negative 17 electron volts. And so
Okay.
I'd be curious to know how we harvest it for use in nuclear reactors today, or if we actually manufacture it. Maybe you can look that up on Wikipedia for me and let me know Monday.
Yeah, that's what I was about to do actually.
There's this really cool movie, Moon, with Sam Rockwell, and I think they're harvesting. I forget what they're harvesting. I think just heavy hydrogen on the moon, for fusion
What's the movie?
reactors. Yeah, MOON. Yeah, it's sad but very poignant. Sci-fi movie about mining on the moon for power.
A lot of power up there.
Yeah,
Thank you very much.
Yeah. Keep up the good questions. I like these interesting things that make me reach too. Now I'm curious how to get deuterium.
In my high school, I was the one who asked the too many questions that people would start to sigh. And so I'm going to try to keep it not at that level. But
Yeah, no, this is fine towards the end of class, and so far there's been no issue with too many questions in this class. So yeah, keep it up.
phenomenal. Have a nice day.
Adios.
Hey,
Do we utilize? Oh yeah, go ahead.
I completely forgot about the quizzes. Is that all right if I just get both those done right now and then submit them?
Yeah, I think it's just one quiz. Yeah, get it in.
Okay, cool.
Yeah, get it in this weekend. Yeah.
Okay,
no.
awesome. Thank you.
Yeah, it's just to force you to read the Asimov short story.
Okay, cool.
Yep.
Thank you.
Do we utilize, is Jonathan still here? Yeah, he is. Do we utilize the law of quantum mechanics to create more efficient systems? And is that direction you see the study of energy going? Yes, we certainly do that for computer chips. We definitely use quantum mechanics to develop much more energy efficient computation. And computation is exponentially growing in terms of its energy use in society. So yes, absolutely. And also we use it a lot in electrochemistry, so fuel cells, batteries, those sorts of things, and carbon capture and the assembly of different fuels. So different people are thinking about trying to pull CO2 out of the atmosphere and use various catalysts to separate the carbon from the oxygen, and then combine that carbon with hydrogen to make so-called renewable biofuels. So make methane and acetone and different things like that from carbon out of the air, with obviously an energy input. But if the energy input's wind or solar and you're making these fuels, then that's the way you can make renewable fuels. And yeah, that's all quantum level stuff. And you have to talk to a chemist, not me. I don't know how that works.
Wait, so would an energy major would this like an energy major would kind of have like principles of like physics and chemistry and like
Yeah, that if you go into energy sciences, yeah. You'd want to talk to Tim Kowalczyk. He's a chemist at Western that studies all sorts of quantum level things for harvesting energy. Also, David Patrick does that too. He makes solar panels that are transparent that you can paint onto a window using these things called quantum dots, which are arrangements of atoms that allow the trapping of a photon and then transmitting it back out again. Again, it's beyond me, but
wait, so is that like on the quantum level? Like they constructed it
yeah, at the quantum level, at the nano level. Yeah, Google quantum dots.
Okay.
And you can use them to either absorb photons or emit photons. So Samsung has a line of televisions that emit very vibrant reds and blues using quantum dots.
And wait, what were the professors' name again? Like, or the
David
and-
Patrick and Tim Kolowzik. I forget how to say his last name, but if you Google like WWU chemistry department, you'll see those names and you'll be able to reach out to them. But if you did like a independent study with Tim, that'd be awesome. David's pretty busy because I think he's like dean of graduate studies now, but Tim should be available. But he's super smart and hard worker. So if you're lazy, don't contact him or you'll be embarrassed. I'm usually embarrassed when I'm around him.
I think of myself as a hard worker, but I kind of get like stressed out sometimes, so I become like avoidant or anything.
Get over that. That's it just think about like what are the alternative outcomes, right? If you reach out and work, then something good is happening. If you get stressed out and paralyzed through your fear, it's something that happens to all of us. It certainly happens to me all the time. Then, another day, another week, another 2 weeks goes by and nothing happened. And what was gained from that worry? Absolutely nothing. So just let it wash off you and realize that, we're all humans and doesn't matter in the end. So do something interesting with the time you have.
Oh, also, like, what other classes you teach? Like in this is Energy 101. What's like the next course?
The next course, unfortunately, it's a little too similar. We're trying to revamp it a bit, but would be Energy 380, which is energy in the environment. So that really focuses on environmental harm from our energy systems. But then all the energy science courses that people like Tim teach be like Energy 320. So that looks at the physics and chemistry of things. Just basic chemistry and physics classes would be important to take. Things like thermodynamics. If you want to get into fuels and things like that, then organic chemistry would be super important. If you go to Google, let me share a different screen here. Where's my, Can you see my screen? So if you go WWUIES, that stands for Institute for Energy Studies. You click that, and then programs. So we have BA, BS, minors. So we did Energy Science and Technology, BS degree. There should be, where's the flow chart? Thought there used to be like a PDF. I'm gonna open this with another tab, see what that does. It's packed, like 111 to 118 credits, so it'd take a while to parse through. There used to be this cool like flow chart, and I'm not seeing it anymore. Gail, she'd be a wonderful person to talk to. She can give you that flow chart. What it does is it says what you should be kind of taking each year and what prerequisite classes you need to get to the next classes. But the way in general, the way it's constructed, maybe this is a better place to look at it, is you need some requirements for the major. And so this is like some energy and geology classes. And then you need these fundamentals. So if you're early on, what year are you?
I'm a freshman.
Okay, cool. So you want to be looking at this math and science fundamentals. To get into the minute. So you need things like calculus, you need things like physics, some chemistry, organic chemistry. And then you can, little CS would be beneficial, but they can be traded with math classes, things like that. And then to my chagrin, because I think I'll keep my mouth shut. You have to take some economics because energy is a people problem too.
It is.
And so understanding how people behave and how economies work is going to be critical to actually solving some of these energy problems. And so a few econ classes that you'll need to do. And these can be helpful because they can help you get like writing proficiency credits and pad out some of your GURs and that sort of stuff.
Yeah. Because
And then later on is all the real fun stuff. So here's another class I teach: greenhouse gas mitigation. Calculate, how much by doing different things like swapping out a light bulb, like I talked to Tay. How much money would you save? How much carbon would you save? And what if an entire city did that or an entire nation did that? Yeah, and then a bunch of different electives. Yeah, but it's good that you're so early on, so you can really start to map this out. And talking to Gail would be crucial. She's wonderful. She'll keep a file on all the students interested in energy, and she'll help tell you what classes you should probably take next quarter to stay on track, or even graduate early if you want to.
Yeah, I was hoping to try to graduate in like 3 years, but I don't know how feasible that is.
Yeah.
But yeah, because originally, or maybe still am, I don't know, but I was looking to go into the physics major, and there are kind of some interlap like of requirements, but like
all the math and stuff is very much intertwined.
but being in class makes me realize that maybe I'm leaning more towards energy, because I've always kind of been invested in it. Like I was kind of like trying to ponder like if and how like it would be to reverse the effects of climate change, or what we can do. So if something like this existed when I was an undergrad back in the early 2000s, I totally would have done it. And it's pretty special. Like this doesn't exist many places. Like there's an undergraduate energy program at MIT, Stanford, Colorado School of Mines, and here. Yeah.
So.
Oh yeah. Huh.
And then really good energy grad schools would be Berkeley, MIT, UC Berkeley.
Yeah, it also popped up for a really good physics grad or school, whatever.
Oh yeah, 100%. So look at where some of the professors here went to grad school, and that can give you a good idea. So like Tim went to MIT, Imran Sheikh and Froilan Cifuentes both came out of Berkeley. I came out of Stanford. Joel came out of Stanford. So I think those are, maybe I'm biased, but those appear to be like good energy places.
Yeah.
And we're building it up too. We are now a good energy place. We just don't have a grad program. You can get a master's here, and you're welcome to.
Yeah, I'm not too concerned about the grad right now.
Yeah.
I heard like that over at UW. It's like a good school, but a lot of the focus goes into the grad program. So if you're an undergraduate, you don't get that much attention and everything.
Nope. Yeah, I was an undergrad at UW, and I never saw a professor face to face. Nothing like this ever happened. That's for sure. Cool.
All right, I'm gonna go because my siblings are calling me.
Sounds good.
Yeah. Thank you though.
Yep.
All right. See you next time. Bye.
Yeah.